All right, there's two things we got to go over today before we pick up with our next section. The first of them is this little piece of paper I handed out to you, the Seton Hill University form. This is AP/CHS Calculus. Okay, so you have different options as to how you would like to obtain college credit for being in this class. You can either go the AP route, which involves taking the AP test at the end of the year, or you can go the CHS route, okay, college and high school, which is through Seton Hill. Now, you have to do one or the other. You can do both, but you have to choose one option as a part of being enrolled in this class. Okay, so I'll go over the two options and you can choose for yourself which one would be the best for you. As far as the AP test goes, the only way you get college credit through AP is if you pass the AP exam at the end of the year. It does not matter what or how you do in this class. You could get an A, you could get an F. Okay, as long as you pass the AP test, you will most likely gain college credit. Now, it depends where you're interested in going as to the minimum score that they accept. I don't know if you guys are familiar with AP or not, but it's scored from a 1 to a 5, 5 being the best, and a 3 is considered passing for AP. Okay, that's their standard, but some universities have a little higher standard and they require either a 4 or a 5. For instance, Pitt and Penn State, they require a minimum of a 4. I know Clarion and I think IUP, they require a 3. Okay, so it depends on where you want to go as to that minimum score. The high school pays for your AP exam, so you don't have to take anything out of your pocket or your parents' pocket for the AP option. Okay, the CHS option through Seton Hill is a little different. Okay, how you gain college credit that way is if you pass this class, I believe it's a C or better, you automatically get college credit. There's no test at the end of the year. It's just how you do in here is how the credit would be for Seton Hill. Now, if you're interested in going to Seton Hill, that's wonderful because your credit and grade would just transfer. But if you don't want to go to Seton Hill, you have to make sure that whatever college or university you're interested in accepts Seton Hill transfer credit. If they don't, this might not be the best option for you. Do you understand that? Okay, so the Seton Hill route, you do have to pay something. Okay, the high school does not cover this cost, and it's $200 or $220. Okay, for the course. That's either out of your pocket or your parents' pocket. Okay, so there's a little give and take for each option. You can either pay the money, and in my opinion, this is the easier way to get college credit, or you don't pay the money and you try very hard on the AP test, which can be a little bit more difficult. It's free, but it's difficult versus paying and a little bit easier. Okay? You can do both options. Okay, maybe you're not sure where you want to go just yet. Maybe you don't know if the university even accepts AP credit or Seton Hill credit. You could do both options just as a backup. Okay? If you are interested in Seton Hill though, you have to make sure you read the directions. Make sure, this is the website you have to go to register. It didn't really show up neatly, so I'm going to write it on here. It's grif.ly/CHS and then Freeport. All right, you have to go to that website to register through Seton Hill. And registration is open until September 28th. So you do have this deadline to kind of choose whether you want to go this route or not. Okay? So once this date comes and your name is not on their roster, that's telling me that you are definitely taking the AP test. You understand that? You have to choose one or the other. You could do both, okay, but definitely one or the other. It goes into some other options. I'm not sure if you're enrolled in any of these other courses, but these are other classes that are giving credit through Seton Hill. Okay, you would have to pay an additional $220, okay, per course. But these are some other outlets you can go through for different classes. Any questions on that? Okay, so you have a good month to decide if you want to take the CHS route. Okay? All right, the second thing I want to cover, remember this title page I handed out the other day with all your notes? This is on page 11. Okay, we officially finished our first section, okay, kind of our introduction to limits. We were working on some of the homework problems yesterday. We're going to get into the second section, a little bit more with limits, but this time we're going to look at equations more than the graphs and the tables. And notice how as soon as we're done with this section, which I think might only take 2 days, okay, it probably will take 3 because we have shortened periods tomorrow, right? I think we have that assembly or pep rally. So this might take 3 days, but as soon as we're done with that section, the next day we're going to have our first partner quiz, okay? Now, I'm not going to get in the habit of warning you guys when things are happening, okay? You got to make sure that you pay attention to where we fall on this little timeline, okay? But just as your first heads up, anticipate a partner quiz sometime next week, okay? Yeah, Dan?
I'm noticing that the Unit 1 exam only has 7 multiple choice.
Yes, okay, so on the AP test, each multiple choice question has an average time of 2 to 3 minutes, and each free response question has an average time of 15 minutes. So 7, I give you 3 minutes, so 7 times 3 is 21, plus 15 would be the 36. We have a 45-minute period, so I'm kind of giving you 10 more minutes than you would actually have on the AP test. Okay? Now maybe you could have a personal goal to try to tackle it within that 36-minute time frame. Okay? But since we're still learning and getting used to things, I figured that 10 minutes would be a good option. Okay? When we get towards the end of the year and we start doing practice tests, we're definitely going to stick to the AP timing though, just to get used to it. Anything else for the cover page or timeline? All right, let's start section 2. We're on page 25. So up to this point with limits, we've been looking at table of values and graphs, but we're going to start to get into some equations first, or in this section, some equations. So look at the top, consider the absolute value function given there. The graph is to the right, and based off the graph, we're going to determine the following limits. So we have this little organized table here to help us out. The first limit is asking us if we were to approach 0, right? This is what we're trying to figure out. If we approach 0 from the left and the right, you see how we don't have those pluses or minuses? If we were to approach 0 from the left and the right, what height would your graph have? -2, right? 0 from the left, 0 from the right, we're approaching -2. So the limit value based off the graph is -2. Okay, we're going to do all the limits first, and then we're going to fill out this other column here. What about if you were just to approach 2 from the right? What's the height of our graph getting closer to? Good, Ariana? -4. All right. And if we were to approach 10, oh boy, that's off our graph, right? You want to give it a shot?
4.
Okay, maybe. We'll say 4 question mark. We'll see if that's right or not. Okay, so based off the graph, we could definitely answer these two, but this one, not so much. Let's go ahead and check out this column. Find f of a. Notice how a is representing the number that the x value is approaching. So if we were to take 0 and plug it into the f equation, okay, which they give us up here, what would we get out? Let's see, 0 times negative 2 is 0, plus 4 is 4. The absolute value of 4 is still 4, times a half is 2. 2 minus 4, we get negative 2. Let's go ahead and check out the next one. This time the x value is approaching 2. Negative 2 times 2 is negative 4, plus 4 is 0. Absolute value of 0 is still 0, times a half still 0. Minus 4, negative 4. Maybe you're starting to see a connection. So even though this one was kind of off our graph, do we have another method of figuring out a limit? What do you want to do? Can we check to see if this one was actually 4? Go ahead, Ariana. Let's go ahead and plug in 10, okay? Negative 2 times 10, negative 20, plus 4, negative 16. Absolute value of negative 16 is positive 16, times a half is 8. 8 minus 4 is 4. So it looks like graphically, if we were able to extend this out towards that x location of 10, the limit would be 4. Okay, so this gives us another way to evaluate limits. Notice how if we didn't have the graph, okay, we could still figure out the limit value based off the equation, right? They're matching up, they're the same. So when a function is defined, okay, meaning a function exists, and it's continuous. Do you know what that word continuous means? Can you describe it? Yeah?
No breaks such as asymptotes or holes.
No holes, no jumps, no asymptotes. Okay, you see how this graph has none of that going on? Okay, you could literally draw it without lifting up your pencil. Okay, so if a function exists and it's continuous at this particular point, how can we find a limit analytically? Okay, analytically kind of means by hand, using some algebra. How would you describe it? How can we find a limit by hand? What did we do? Yeah.
We take the a value and put it into the equation or function.
All right, plug in a into the f of x function. Do we know what that's called mathematically if you plug something in? Yeah. Substitution. Okay, we're going to substitute in a number. So notice how when we get to some of the examples at the bottom of the page, we no longer have graphs, we no longer have tables, we just have an equation. But now that we know how it works, we can go ahead and try to tackle these. So let's go ahead. If we were to approach 3 from the left and the right, okay, even though we don't have a graph, what would the height of the graph be approaching? Can we figure out this limit? Let's go ahead and plug it in, right? Substitute it in. Okay, you may have some fraction work. You might have to get a common denominator. We can change this to 6 over 2. So 9 minus 6, we got 3 over 2. There's our limit. There's our height. So even though we don't have a picture, okay, we can maybe visualize it. As you come into 3 from the left and the right, the height of your graph is 3.5, or not 3.5, 3 halves, aka 1.5. Okay? So no picture necessary anymore. You want to go ahead and try B? if you were to approach 3 from the left and the right, what would your height be on the graph? Good, Brandon?
17 thirds.
17 thirds. Agree? Perfect. All right. Next one. This time we're approaching 2 just from the left, okay? But in terms of this substitution idea, the left or right don't really mean anything. We're just plugging in that number value. So let's go ahead and plug in 2 and see what the left-handed limit would be. If we were to just come in from the left, what height would we be approaching? One-third. Can we get that? Okay, the square root actually works out nice because you get 4 on the inside. All right, let's go ahead and try a trig one. So if you were to directly substitute in pi over 2, notice how we can multiply that by 2 and that would get rid of the 2's, so we're just left with pi. All right, so unit circle time. If you think about your unit circle and you were to go to the pi location, what is the sign value from that ordered pair? Sign pi, or is all the way to the left? Sign of pi. Or Braden? 0. Okay. So graphically speaking, if you were to approach pi over 2 from the left and the right, the height of your graph would be 0. You'd be on that x-axis. All right, let's go ahead and try another trig one. This one's a little trickier. All right, now 2 pi over 3 is not one of the ones that I told us that we have to be very familiar with, okay, because this is not in the first quadrant and it's not one of the corner points, you know what I mean? Okay, top, bottom, left, right. So if you need to reference this one, that's okay. Okay, you can maybe flip through to try to find that point. But if you were to go to the pi over 3 location on the unit circle and take a look at the cosine value from that ordered pair, what would you have? Yeah.
-1/2.
All right, it's -1/2. How do you divide fractions? Divide by fraction, good, Ariana?
You're going to multiply it, but the second one, or 2 pi over 3 will be
The reciprocal, right. Instead of dividing by a fraction, we're going to multiply by the reciprocal to help us continue solving this one. So we have -3 over 4 pi. Multiply straight across the top, straight across the bottom. Kind of a weird answer, right? It's a fraction with a pi in it, but this is representing a height. Okay, this is representing a y value. All right, let's try the next one. Direct substitution, plug it in. We'd have log base 8. If we plugged in 9, we would then get 2, right? Now logs can be tricky because logs represent some powers. But I'm wondering if we can think, perhaps, what power would you have to raise 8 to get the number 2? AKA, 8 to what power gives you 2? That's what we're trying to figure out. Notice how we're starting with 8 and we're ending with 2, so this is probably going to be less than 1. A fraction or a decimal, yeah?
1/3.
It is a third. Okay, a little tricky. Maybe some of you can use your calculator to help you with that. Do we know how to enter logs in our calculator? Maybe? Maybe not? Log base. Right, good. Okay, so maybe a good quick example here. You got to hit the math button. And we're going to scroll down to letter A. Some calculators have this, some don't. It depends on the operating system you have. I believe most of mine have this one, and if you have a colored edition, yours definitely should have it on there because it's the newest one. So option A is log base, and if you bring that up, we can type in 8 as the base value, and 2 is that it's referred to as an argument, but it just means inside parentheses. And notice how we'll get 1/3. Okay, so there is a way to evaluate that on your calculator. We doing okay so far? Kind of easy, we're just plugging in numbers. Okay, let's go ahead and try some of these on the back. What happens if we try direct substitution on these examples? All right, might take you a little bit of time because there's more x's, but if you were to plug in -3, go ahead and see what your numerator would be and what your denominator would be. What do you think? What happens if you plug in -3 either up top or in the bottom?
There's a 0 on the bottom.
There's definitely a 0 on the bottom. What do you get up top? Yeah.
A 0 as well.
A 0 as well. What's 0 over 0?
Or
It's not 1.
0. Or
It's
undefined.
not 0. Yeah. It's undefined. You cannot divide by 0. All right, this is undefined. Now, 0 over 0 is very special. It has a particular title. It's called the indeterminate form. Okay, 0, specifically 0 over 0, indeterminate form. Now, what do you think this means graphically? Okay, we said the closer we get to -3 from the left and the right, this is representing our height, but our height is undefined. So graphically speaking, if your height is undefined, what is possibly happening graphically at that -3? Yeah.
The ladder doesn't reach it, or there can be an asymptote.
It doesn't reach it, there's an asymptote or a hole. Okay, one of these three things. Okay? What's happening in this case is we have a hole. 0 over 0, indeterminate form, is another way to signify you specifically have a hole at this -3 location. Let's go ahead and check out, so we have the same equations here, but this time we're going to directly substitute in one from the left and one from the right. When you're doing direct substitution, though, the left and the right piece doesn't really matter. You're just going to plug in that number 1. So we should get the same answer for both of these. So if you do one, you actually do both. Go ahead and plug in 1 up top, plug in 1 down below, see what you get.
8 over 0.
8 over 0. All right, so this is not an indeterminate form. Notice how it's not 0 over 0. This is technically a number over 0. But what do you think that's telling you graphically? What's happening at 1? Yeah.
You have an asymptote.
It's a vertical asymptote, okay? 8 over 0 is still undefined. You can't divide by 0. It's just a fact that we have a number up top that's signifying a vertical asymptote, whereas if we have a 0 up top, we have a hole. Okay, slight difference between the two. Now we got to be careful, because just because the limits are undefined, that doesn't mean the limit doesn't exist. It just means we might have to do a little bit more figuring, okay, to help us with that. So for example, here's the graph of the equation that we were just analyzing up top. If we actually were to approach -3 from the left and the right, if we were to approach that hole, what height would our graph have? Can we make a guess, roughly? A half, okay? So notice how up top, the initial limit, when we tried plugging in -3, it was undefined, but notice how the limit actually does exist, because we got a height for it. So we're going to see how we can get around that undefined piece. What if we approach 1 from the left or 1 from the right? We said that was the asymptote. If we approach 1 from the left, we got negative infinity, and if we approach 1 from the right, we got positive infinity. All right. Now we could probably answer this one. What if I said the limit as x approaches 1 of this equation? It would be not, we don't say undefined. Does not exist, right? Notice how the left-hand side approaches negative infinity, the right-hand side approaches positive infinity. Those are definitely not meeting up, so we have a does not exist limit. So we got to be careful. A limit will exist at a hole, but it will not exist at an asymptote. It's all based off of whether you get 0 over 0 or a number over 0 when you do that substitution. Okay? So let's take a minute and think about, well, how can we analytically, okay, by hand using some algebra, how can we determine whether we have a hole or an asymptote? Okay, take a look at this equation we were looking at. How could we figure out if we have a hole or an asymptote? What do you think, Dan?
If we were to factor the top and bottom, we could find common.
All right, let's factor. We're going to try to factor the top and bottom. Okay, we'll eventually do this, but I just want to write down what we can do. So the first thing we're going to do, we're going to try to factor. Once we have the factors, how do we determine if we have a hole versus an asymptote? Good, Ariana?
A whole, a factor will be on the top and bottom, that's the same, and then if it's just asymptote, it will be just on the bottom.
All right, so if you have a hole, you have factors that cancel. And you have a vertical asymptote for a factor that does not cancel. Or factors that don't cancel. You could have more than one. And when we're saying factors, okay, I'm referring to the factors in the denominator. Did not, if I can spell. Okay? Because those are the ones that make the bottom 0. Those are the ones that are of interest to us. Okay? So let's actually go ahead and try that. Can we factor the top and bottom? This is the same example as we've been doing. Same numbers. You get it?
X plus 3, x plus 1 on top, and then x plus 3, x minus 1.
All right, so we factored. Are any of those factors going to cancel? Good, Dan?
X plus 3.
All right, so since x plus 3 cancels, that means the x value of -3 is a hole. And notice how the x minus 1 factor did not cancel. So that means x is positive, equals +1 is your vertical asymptote. No graph necessary, okay, all by hand. So technically, if these x plus 3's cancel, we can simplify this original equation down to x plus 1 over x minus 1. So if we said a limit exists at a hole, let's now go ahead and take that -3 that we just confirmed was a hole, and we'll go ahead and plug it in here. If you were to plug in -3, because if we plugged in -3 at the very beginning, we got 0 over 0. Okay, that tells us it's a hole. But now that we simplified it, let's go ahead and plug it in here so we can get the actual limit value, okay, the actual height. If we were to plug in -3, what? -2 over -4, which is the same as 1/2, right? And isn't that the limit we set up here based off the graph? Okay, so even though substitution may not work initially, okay, if you get 0 over 0, aka a hole, that's signifying you have to do a little bit more work. You might have to do a little bit of factoring and then try plugging it in again. Okay, but if you get a number over 0, vertical asymptote, that's going to be a does not exist practically every time. Okay, because they're going to go opposite directions towards infinity. Okay? We doing okay? All right, let's go ahead and check out some other ones here. So, holes we can check because we get 0 over 0. Okay, let's talk a little bit more about these asymptotes. Okay, based off your knowledge from pre-calculus, we know that a rational function has an infinite discontinuity, aka a vertical asymptote. Since the y values do not approach one specific value from both sides of a vertical asymptote, then the limit doesn't exist. However, we should still be able to determine the one-sided limits. Okay? So in terms of an asymptote, can we determine on the right-hand side, do we go down or do we go up? Okay? On the left-hand side, do we go up or do we go down? So even though as we approach both sides they don't meet up, we should still be able to determine what's going on individually on either side. So we're going to take a look at that. All right, so again, same equation. We already said that this was our simplified form. Remember, we factored it and canceled some things out. So notice how this limit notation is telling you you want to approach 1 from the left. Okay, what are some x values like on a number line that are to the left of 1? There's a lot of them, so you can pick a few. Any one you want. Can we think of some numbers to the left of 1? 0, sure. 0.9, right? 0.1, okay. Now, since we're talking about a limit, isn't a limit the idea of getting very close to something? Like, what are you approaching? So 0 would still work, but do you notice how 0.9 is closer to this 1 value than 0 would be? Okay, so there are a lot of numbers, but the closer you can get to this value, the better it is. Okay, I mean, you could pick 0.8, 0.7, those would be okay too, but we're going to pick some number, any number you want, to the left of 1 that's fairly close to it. If you were to take this number and plug it in to your simplified equation, let's see what we get. All right, 0.9 plus 1. Is that value positive or negative? I don't care about the number. Is it positive or negative? 0.9 plus 1. 0.9 plus 1 is positive. What about 0.9 minus 1? Yeah, just the top, sorry, just the top. 0.9 minus 1, positive or negative? Negative. What's a positive divided by a negative? Negative. All right. So, what do you think, what direction is the graph going on the left-hand side of this asymptote? Do you think I need to draw a graph going up or a graph going down? down, right? Negative, makes sense. Okay, so graphically speaking, on the left-hand side of 1, okay, this x value of 1, our graph is going down. So in terms of the limit, we would say this equals negative infinity. We're going to do a very similar process, but notice in this limit, we want to approach 1 from the right. So you want to pick a number that in this case is bigger than 1, but still fairly close. Okay, I put in 1.1, you could do 1.5. Okay, something fairly close. If you were to plug in that number into your simplified form, we're just looking at positives or negatives, aka the direction we're moving. 1.1 plus 1, positive. 1.1 minus 1, positive. Positive divided by positive, still positive. So if our asymptote is at the x value of 1, the right-hand side is growing upwards. So this limit would equal positive infinity. So to evaluate limits at a vertical asymptote, you have a little figuring to do. Okay, what's going on the left-hand side of that asymptote, what's going on the right-hand side. Okay, but it's up to you to pick these numbers, something fairly close. We doing okay? All right, let's go ahead and amp it up a bit. Let's look at a square root one. All right, the graph of the function is pictured to the right. Often rationalization can be used to evaluate a limit analytically, aka by hand. So we're going to try to figure out this one. So the limit as we approach 3 from the left and the right, okay, what does that equal? Can we possibly determine what that might be based off the graph? If you were to approach 3 from the left and the right, can we take a guess as to where that hole might be? What does it look like to you? 1/4. A third, maybe a fourth, something like that. Okay. So let's do substitution first. Okay. Direct substitution should always be your first guess or your first try, because if you get a number, you're good. If you get 0 over 0, you know it's a hole. If you get a number over 0, you know you have an asymptote. Now we already know what's going on here because we have a picture, but let's say that wasn't there. Okay, direct substitution is always your first bet. So if you were to plug in 3 in top and bottom, what do you get?
0 over 0.
You get 0 over 0. Okay, I'm going to write that over here. 0 over 0 initially. So just off of that analysis, we know we have a hole. And we can see that based off the graph. But just because the limit is undefined, okay, just because the limit gives us a hole doesn't mean the limit doesn't exist. Okay, a limit exists at a hole, so we have to do a little figuring, a little bit more algebra work with this one to get this possible guess that we think. Okay, and we're going to use rationalization. The rationalization process involves what's using a conjugate. Have we heard that word before? Maybe? Okay. Do we know what a conjugate is or how we find it? What do you think? Yeah.
Is it when, like, it's used for imaginary numbers a lot? It's when, like,
It can be, yeah. Mm-hmm.
It would be the x value on the bottom, and you take the opposite sign of the middle and the same number, so it would be x plus 3, and then you just put that on the top.
Okay. That's the idea of a conjugate, where you change the sign, but in this case, since the square root is up top, we're going to use the conjugate of the numerator. Okay? So this would be the square root of x plus 1, and then we're going to add 2. Wherever your square root is located, that's where you're going to use your conjugate. Now, if we multiply that value or that conjugate up top, we have to multiply that same value in the denominator. Okay, we got to keep our fraction balanced. So let's go ahead and see what this is going to lead us to. All right. If we were to take the square root of x plus 1 times another square root of x plus 1, what are we left with? Yeah.
X plus 1.
X plus 1, right? The square roots are going to go away. All right, I wonder if we can do the next part of this in your head. Do you notice if you were to take this square root times 2 and then this square root times negative 2, they would cancel each other out? They're exactly the same, but one's positive, one's negative. So when you're going through that FOIL or distribution process, the outside terms and the inside terms should always cancel each other out because you're specifically using a conjugate. So, if you want to make note of that, when you do the FOIL process, you don't really have to do those two because they'll go away. So if we took the first two terms, we get x plus 1. And if we multiply the last two terms, negative 2 times positive 2, that would give us negative 4. Okay, that's only for the conjugate piece. Now for the denominator, I don't know about you, but I don't really feel like distributing all that stuff through because the outside and the inside pieces would not cancel in this one because they're not the same. So for this case, we're just going to leave it x minus 3 and then the square root factor. Can we maybe simplify a little bit? There's the top, we have 4 minus 1, or 1 minus 4, sorry. Anything going to happen? Go, Stevie?
The x minus 3 will cancel.
Uh-huh, so we're simplified to 1 over the square root of x plus 1 plus 2. Okay? So even though we tried direct substitution at the beginning and it didn't work because we got 0 over 0, let's try direct substitution again now that we simplified it. Okay, so if you were to plug in 3 now, what would you get? I think I heard it, 1/4. Right? So we were pretty good there with our guesses. All right. We'll pick up there tomorrow. Deal?
Dang it, Mrs. Bauer.
Dang it.
Yeah, the square root's at the bottom.